been waiting for this very exciting video, so let's get to the problems. All right, so first one. Now, it says the probability of, what is the probability that both girls will get a hit next time at bat? So this is independent, right? So there's two events happening, Tracy going up bat and Selena going up bat. Completely. One has no effect on the other one. It's not like, right, when she goes, I don't know, Selena's going to take a bat, put it in her pocket. There's none of that happening. So this is probability of Selena getting a hit. Oops, can't spell Selena, just fine. And Tracy, they both have to, what's the probability of they both getting a hit? The probability of Selena getting a hit is 8 out of 20. Probability of Tracy is 6 out of 16 based on past performance. And you get, well, 48 over 320. And I'm looking at the answer right there, and I don't, weirdly enough, we didn't simplify this, which is fine. Okay, so if you did simplify, just look at the answer, not simplified. 2. Probability of the Cubs winning their first game is 1 out of 3. The probability the Cubs win their second game is 3 out of 7. What's the probability that they win both games? So just like the previous problem, the probability of winning both games, right? Win both games. So the probability of the first game is 1/3. The probability of the second game is 3/7. We can simplify, and that's 1 over 7. 3. The probability that the bus on time is 2/3, and the probability that Mr. Corney is driving the bus is 4/5. What's the probability that on any given day, Janelle's bus is on time, Mr. Corney is the driver? Okay, so this one also deals, remember, complement, right? We talked about that. So think about the complement because you're going to need. So if 2/3 chance that the bus on time, so all right, if there's a 2/3 chance that it's on time, what is the chance that it's not on time? Well, it has to be the complement, which is 1/3. So now if you add those two, notice that it equals to 1, right? It's 3 over 3 and just 1. Right? So the complement, the probability of something happening, its complement not happening, will always add up to 1. Why do I need this? Because it actually says, what's the probability that on any given day the bus is on time? Oh, sorry, I misread it. So the probability that it's on time is 2/3. And the probability that Mr. Corney is driving that particular day is 4/5. Can we simplify anything? No. So 8 out of 15. Okay, so again, that would be independent, right? I think I was thinking this. Probability that it will rain tomorrow is half. The probability that our team will win tomorrow's game is 3/5. Oh, which expression represents the probability that it will rain and that our team will not win the game? Okay, so here's what I meant by the complement. We're going to use it here. So the probability of rain, right, the P of rain is a half times, right, the probability of not winning. Well, we know the probability of winning is 3/5. So the complement, the not winning, would be 2/5. So the expression that we're going to use is this one. Okay, the probability of the first event times the probability of the second event. Quite easy, right? 5. School day. The probability that Nick oversleeps is 48%. Probability he has a pop quiz is 25. Assuming these two events are independent, which they are, what's the probability that Nick oversleeps and he has a pop quiz on the same day? Okay, so the probability that he oversleeps, so we want 2. The probability of oversleeping and pop quiz. So the probability of him oversleeping is 48%. We're going to write that as, I'm going to write it as a fraction, 48 over 100. Okay. And then the probability that he has a pop quiz is 25 over 100. We'll change it to percent in a second. So let's simplify. This becomes 1 over 4. 4 and 48 becomes 1 over 12. This can be 6 over 50, which I'm going to simplify to 3 over 25. So if you multiply it out, we're left with 3 over 25, and 3 over 25, right, out of 100, we can change this to an equivalent fraction, times 4, times 4, so that is the same thing as saying 12 over 100, which is 12%. Okay, or you could have, again, if you want to do with decimals, change 0.48, 40% to 0.48 and 25% to 0.25, and multiply those out, and then change it to percent. That doesn't really matter. 3 coins are tossed. What's the probability that you get 2 heads and 1 tail up here? So it's independent. You want head on the first, and then head on the second, and then tail on the last, right? The probability, of getting head is 1/2. The second coin would be 1/2. And getting tail on the last coin would be 1/2. 1/8. Can I give you too much of an easy problem here? 7. What is this? What's going on? Okay, so again, this is just another way of saying 2 independent events, right? What's the probability of A times probability of B? So 3 1/3 times 5 over 12. There's nothing to simplify. We just get 5 over 36. Yikes, how boring. Change these questions for tomorrow. 8. Probability that it will snow on Sunday is 3/5. Probability that it will snow on both Sunday and Monday is 3/10. What's the probability that it will snow on Monday if it snowed on Sunday? So here's a little tricky question. So the probability of, let me write this on, that snow on Sunday and Monday, right? It's the probability of Sunday times the probability of Monday, and that gives us an answer, right? So they're telling us that the probability that it will snow on both days, when you multiply this times this, is 3/10. That's what they're telling us. And they also told us the probability on Sunday is 3/5. Okay, so what they're asking us is this spot right here. What's the probability that it will snow on Monday? Well, if the probability of both happening is 3 over 10, and the probability of Sunday is 3/5, how do we figure out this number here? Well, we can do 3/10 divided by 3/5, right? I mean, think about, let me put this in the multiplication. 4 times blank equals 20. How do we figure out this number over here? We do 20, right? Remember fact families from like 2nd grade? We can do 20 divided by 4, and we get our mystery number, which is 5. So likewise here, 3/5 times blank equals 3/10. Right? To figure out that number, we can just divide. So 3 over 10, right? It's a division of fraction, so we're going to multiply by the reciprocal of our second fraction, right? So 3/10 times the reciprocal of 3/5 is 5 over 3. Simplified, that becomes 1. 5 over 10 is the same thing as 1/2. And there we go. So our final answer is 1/2. And just to prove, probability of snow on Sunday 3/5, and the probability of snow on Monday is 1/2. Do we really get 3 over 10? Well, 3 times 1 is 3. 5 times 2 is 10. Ta-da! Finally a good problem, right? Sorry about that. Number 9. The probability that a student owns a dog is 1/3. The probability that the same student owns a dog and a cat is 2/15. Determine the probability that the student owns a cat. So again, this is like the same problem. So what's the probability that someone in class owns a dog and a cat? Right? So it'd be the probability of owning a dog times the probability of owning a cat equals the probability of both. So the probability that a student owns a dog is 1/3. The probability of owning a cat, we don't know. It's not given to us. But we know the probability of both of them happening is 2 over 15. Can we find, again, our mystery number here? What's the probability, right, of only a cat again. So we're divide 2 over 15 divided by 1/3 is the same thing as 2 over 15 times the reciprocal, 3 over 1. Let's simplify. 3 and 15 becomes 1/5. So our mystery number is 2/5. And you can tell 1 and 2 is 2, and 3 and 5 is 15. Number 10. Student Council has 7 officers, of which 5 are girls and 2 are boys. Okay, 2 officers are chosen at random to attend the meeting with the principal. What is the probability that the first officer chosen is a girl and the second is a boy? Okay, so let me just separate this. So 5 girls, oops. Yeah, 5 girls currently and 2 boys. So what's the probability that we first choose a girl and then there's 7 total, right? So what's the probability of selecting a girl? Well, the probability of selecting a girl is 5 over 7 times, well, if we selected a girl, right, we won't have 5 girls anymore. We're gonna have 4. So the girl selected. I tell her to stand here on the side because we already selected. We go back. Now we gotta select a boy. Probability of selecting a boy is 2, but not over 7, right? Because we already selected a girl. It's gonna be 2 over 6. Multiply that out. Let's just simplify. This becomes 1 over 3. It becomes 5 out of 21, or they didn't simplify and they actually left it at 10 over 42. And here's the answer. 11. Bob and Lakeisha have volunteered to serve in the junior prom. The names of 20 volunteers, including them, are put in a bowl. Two names are randomly drawn from the bowl without replacement, meaning if you take a name out, you don't put it back in the hat or the bowl. What is the probability that Bob's name will be drawn first and Lakeisha's name will be drawn second? Okay, so we don't know how many boys and girls. So it has nothing to do with that. It's just a bunch of names. So we want the probability of Bob and then the probability of Lakeisha. So what's the odds that those two can be pulled up? So probability of taking Bob is 1 out of 20. Selecting Bob, he has 1 out of 20 chance to be selected times. So let's assume he got selected. We go back to the bowl. Well, the probability of getting Lakeisha's name is 1 because her name is only written once, but we don't have 20 anymore. We have 19. So the expression is this. And is there an expression? Yeah. Right here. 12. Mr. Yi has 10 boys and 15 girls in math class. He chose his 2 students around to work on the blackboard. What is the probability that both those girls are chosen are girls? Okay, so if he selects a girl to go to the board, he can't select her again. So this is dependent, right? So it's like almost like getting a card and leaving it on the side and going back to the deck of cards and selecting another whatever card, right? You can't be chosen again because you want 2 girls at the top. So probability of girl and girl. So what's the probability that one? Well, we have a total. Always nice to know the total. Total is 25. So the probability of choosing a girl on the first try is 15 out of 25. Right. So we have, and we put Nancy. So Nancy is going to the board. We go back, right? We go back to the bowl. We're going to select another girl. Well, Nancy can't be selected anymore. So instead of 15 girls, we have now 4. Instead of 25 people in total, we now have 24. And that's what we're going to multiply. Let's simplify here. This is divided by 5 is 3, divided by 5 is 5, divided by 2 is 7, divided by 2 is 12, and then 1, and this is 4. Can we simplify anymore? No. So 7 out of 20th chance that 7 out of 20 chance that we can select a girl and a girl. There are 4 students, all of different heights, or randomly arranged in a line. What is the probability that the tallest students will be the first in line, and the shortest students will be the last? So the probability of the first, what is this, 13? tallest first in line. I guess I'll write that first in line. And then what's the probability that the shortest will be last in line? Right, so what's the probability that the tallest guy will be in first in line? It would be 1 out of 4, right? There's a 1 out of 4 chance of the tallest person to be in the first spot, times what's the probability of the shortest person being in last in line? Well, the tall guy can't be counted anymore, so there is a 1 out of 3 chance that the shortest guy will be last in line. So, final answer, 1 out of 12. 14. 6 apples, 5 oranges, 1 pear. I'm just going to add them up. 6, 5, and 1. That's 12 total. In the basket, his friend takes 3 pieces of fruit at random without replacements. Takes them out of the basket, doesn't put them back. What's the probability that all of them are going to be apples? Well, so it's going to be P of apple, followed by an apple, right? You're going to take an apple in a second, and then another apple. So this is dependent because it will change. Not putting that apple back will change your total. So first one, probability of getting an apple, 6 over 12 on your first try. Let's say you took the apple. Here's the apple. Let me put it over here. Go back to the basket and want to take another apple. I don't have 6 apples anymore. I have 5. And I don't have 12 in total. I have 11. So I take the second apple, put it over here. And then I go back for a third try. I want to get another apple. Well, it's no longer 5 apples. It's 4 apples. And no longer 11 total. It's 10 in total. So that would be the probability of getting an apple, followed by an apple, followed by another apple, right, without replacement. So let's simplify. 1 and 2. This is also 1 and 2. This is a 1. This is a 2. This. So we have a 1 out of 11 chance of this happening. 15. Vince buys a box of candy and consists of 6 chocolate pieces, 4 fruit, 2 mint. He selects 3 pieces of candy at random without replacement again. Takes the candy, eats it, can't put it back. What's the probability that the first will be fruit? So probability of getting a fruit. And then the other 2 will be, so fruit, mint, and mint. That's what we want to calculate. So what's the problem? Well, let's get the total first. 6 chocolate. Let me write 6 chocolate. 4 fruity. And 2 mints. So the 2 mints we have, so there's a 12 total. So probability of fruit, getting a fruit on the first try is going to be 4 out of 12 because there's 4 fruits and 12 in total. I take 1 fruit, put it here on the side. I'm going to go back, try to get a mint this time. There's 2 mints, so it's going to be 2, but it's not going to be 12 because I took 1 fruity one outside and I'm left with 11. So next to fruit, I'm going to put a mint. So actually, what I should have maybe do it's easier. 2 mint, right? And we had a total 12 total. So I took a fruit out. Now I'm left with 3. I took a 1 mint out. I'm left with 1. So on the third one, I'm going to reach my hand into the bowl bag, and I'm going to get a mint. Try to get a mint. There's 1 mint now, and you can tell that there's a total of 10. So those are the 3 that I'm going to multiply. Let's simplify. 1 and 5, 1 and 3. So it looks like 1 out of 33. 33 times 5. 15 goes 165. There's a 1 out of 165 chance of me accomplishing that. Not that big of a chance. Okay, so that's the first answer. And then there's 2 questions in this problem. So the second question is calculate the probability that all 3 pieces will be the same type of candy. Ooh. So the second one's a little bit more. So let me write this. 6 chocolate, 4 fruit, and 2 mints. Now the second question says calculate the probability of getting all 3 pieces, that all 3 pieces will be the same. Well, it's only going to work for the chocolate and it's only going to work for the fruit because I don't have enough mints. So this one's going to be a little bit different. So what's the probability of getting chocolate and then the chocolate and then the chocolate? So that's one experiment right here. Plus the probability of getting a mint, sorry, not a mint, a fruit, oops, and a fruit, and a fruit. So this one's a little bit different. The probability of the chocolate is going to be 6 out of 12, then 5 out of 11, and then what is this? And then 4 out of 11. Four out of 10, I apologize. Plus, now here's the thing though. Do we assume that the chocolate are gone? No. And then the probability of getting a fruit would be 4 out of 12. And then, so this is the chocolate. And then 4 out of 12 plus 3 out of 12. 3 out of 11, I apologize because 1 is gone. Plus 2 out of 10. So that would be what we need to do. Ugh. Let's see if I can simplify this. That's a half. So let me simplify. That's a half. That's a 2. 1 and 2. This is gone. So that becomes, looks like 1 out of 11. And this, again, this becomes 1 out of 3. Those 3 goes away. This is 1 out of 5. So this becomes 1 out of 55 plus 1 out of 55. We can add these two, so let me just make it a little bit better over here. 1 over 11 plus 1 out of 55. This becomes 55. 5 on top. 1 out of 55. 6 out of 55 is our answer. It's either 3 chocolate or 3 fruity ones. Okay, that's why we added the probability of 3 chalk plus the probability of 3 fruits. Okay, and that's what we just did right now. 16. A bottle contains 12 red marbles and something, 8 blue. Marbles chosen at random and not replaced, so we're not putting it back. Then a second marble is chosen at random. Determine the probability that these 2 marbles are not the same color. Ooh, interesting. 12 red, 8 blue. So, first question, determine the probability that not the same color. So if I choose probability of red, and then the second one has to be a blue, right? So what's the probability of getting a red? The probability of getting a red is 12 out of 20. And then the probability of getting a blue is 8 out of 19. Remember, we took, right? And plus, right, and there's another, or we can have probability of blue first and then getting a red. So the probability of blue is 8 out of 20. Okay, and then the probability of red would be, of getting a red would be 11 out of 19. And these are the two that we have to take care of. And actually this, and then let's see if I can simplify this. No, well actually I won't simplify yet because I'm going to have to add these two. So 320 times 19 is 380. So on this side again, 12 times 8 is 96. So we get 96, bring it over here, 96 over 380 plus, what is this, 88? Oh, I made a mistake here. Probability of red is 12 over 19. I apologize. Plus 8 times 12 is 96 again. Over 380. We're going to get 192 over 380. Okay. You can go ahead and simplify that if you want. 17, a jar contains 5 red and 3 green. A marble is drawn at random and not replaced. The second marble is drawn from the jar. Find the probability the first marble is red, the second marble is green. Okay. We have 5 red, 3 green. Second marble is drawn. Find the probability. So we want the probability of red and then green. So let's do that first. This is 8 in total. So the probability that the first one is red is 5 out of 8. The probability that the second one is green would be 3 out of 7. Remember, it's not replaced, so we've got to make sure of that. That gives you 15 out of 56. Then we had, find the probability that both are red. Well, P of red and red. And we're not returning the marble, so again, there's 5 red and 3 green. So the probability of getting a red on the first try is 5 out of 8. But you put a red over here, you go back in the bag, you don't have 5 reds anymore, you have 4 reds out of 7. Okay, and like, can we simplify? Yeah, we can. 2, and we get 5 out of 14. Okay. Find the probability that both marbles are the same color. What do they mean by that? So it either could be both red, right? Or, and here's the or, so anytime we see an or, we're adding, right? Or that both ones are blue. Blue and blue. So the probability that both are red, we just did that, right? We got 20 out of 56. Okay, so I'll just do it again. The probability of, and again, there's 5 red and 3 green. So the probability that both are red is 5 out of 8 times 4 out of 7, right? And that's going to give us 9 out of, sorry, not 9, oh my God, 20. I'm going to simplify. So this is 1, this is 2. We get 5 out of 14. We just did that. Plus, both are blue would be, not blue. I don't know why I meant to say green. Right, so there's probably that both, it's a green and green. So it'd be 3 out of 8 times 2 out of 7. Well, I can simplify. This becomes 1 and 4, so that's 3 out of 28. We can just add those two now. Find common denominator. This is 28, which becomes 10 out of 28, and 3 out of 28. Final answer, 13 out of 28. Do 13 out of 28. Okay. Oh, take that back. Nice little problems. 18. Throughout history, many people have contributed to the development of math. These include Pythagoras, Euclid, Hypatia, Euler, Einstein, Agnesi, Fibonacci, and Pascal. What is the probability that a mathematician name selected at random from those lists would start with either the letter E or the letter A? So, how many people do we have here? 1, 2, 3, 4, 5, 6, 7, 8. So the probability is going to be out of 8, and we want so think about it, if you pull anybody who starts with an E or you pull anybody who starts with an A, you're a winner. So you got to include. So we're going to add those two. So E would be Euclid, Euler, Einstein, and then A, Agnesi. There's a 4 out of 8 chance of you accomplish that. So if you pull out any of those names from a hat, you win. And there's your answer. Okay. All right. Let's take it back.